All right. I guess it's lecture 8. And welcome to lecture 8. Today I'm going to cover the materials on oscillators, and I believe few problems left from the mixer design. I will solve those. Also the questions from the assignment 1. I'm going to give you the answers and how to solve them. Most of you did it well. It was very good. And then just, thank you very much. And then just, if we got time, then I'm going to solve the questions for the oscillators as well. Before I start the topic, so the assignment 2 is available, and please consider that and submit it by the end of next week. So there are 2 questions, and the question 1 is just simple calculation of a Z-in for a BJT with a degenerative reactance, while the C pi and C mu are not 0. I mean, just consider that these 2 are. Do not neglect those, and then calculate the impedance. And then in the second question, so in the first part, you need to design a matching circuit using a Smith chart. So design it on the Smith chart and then upload your Smith chart. And then in the second part, you need to simulate the circuit in one of the software, LTSpice or ADS, any of them is fine. And then just upload the result, I mean the graph. You don't need to upload the file, the design file. Just upload the graph that you got. About the gain of the transistor from DC to 2 gigahertz. And just write down, for example, that, okay, what did you understand from this graph? Any question? So anybody did try this before? Till now? No? Okay. All right. So before you get tired, then I start the oscillator, and then at the end of the class, I'm going to solve the questions. I think this is better than that. So I gave you a brief about the oscillators in the previous lecture, but just to start from the beginning, oscillators are one of the fundamental components in the transmitters and receivers both in the RF circuits. So if I just So again, if I draw a receiver part, and transmitter is something that I did before. So a receiver part, again, we have one antenna, and then after the antenna, we put a band pass filter, which filter out the undesired signals that we want, and then after this, we have usually we have one LNA, and then the next stage of this is a mixer, which we covered in the previous topic, and this mixer has a signal which comes from a local oscillator. And then after that, again, maybe we have another band pass or low pass filter, and then a low frequency amplifier, and then the signal is going to ADC. So this is your ADC and then the processor. So to your microprocessor. So this local oscillator we use in the receivers to down convert our signal, and in the transmitter to up convert the signal. What you should consider is that sometimes we use a IQ modulator or demodulator. So then we use oscillator and then two mixers. I mean, we use two mixers and then again use this signal, but this oscillator, the output of this oscillator is passing through a 90-degree phase shift and then use as the LO, and then the rest is the same as the other one. So we get two signals in the wireless communication. Mainly we use this architecture, and then the rest is the same. So why we use I and Q? So this is your RF signal, and this is your IF, for example, I and IF of Q. Why we use IQ signal? I mean, why these two are more important? Instead of having only one of them, why two of them is more convenient for us? If we have two of these, instead of only having one of these. Because with one of these also you can find the signal. I mean, you can find the IF signal, and then based on the IF signal you can detect that what's the signal. Why we use I and Q usually? Because it is much simpler in the signal processing to recover your signal. I mean, then the gain of your signal is always I squared plus Q squared, and then the phase of your signal is tan minus 1 Q divided by I. Okay? So it's much simpler in the signal processing to recover the main signal if we have the I and Q at the same time. Mainly in the wireless communication. So you can see that this component is a fundamental one, and we need it. The same thing in the transmitter. So again, we need this component to up-convert our signal and then transmit it. So no difference. Just assume that the signal is passing this way. So you have a D2A and a filter, amplifier, and then up-convert the signal, amplify it, and then send it through the antenna. Okay? So how to make an oscillator, or what are the types of oscillator, if I want to tell you. So mainly we have two types of oscillators. I mean, we categorize the oscillators as the switching oscillators and linear oscillators. So these are the two main categories of the oscillators. In the switching oscillators, we will see that we use a capacitive component to store the charge, and then after that again we discharge that one. So this is how a switching oscillator is working. But in the linear oscillators, we use a kind of positive feedback to make the system unstable. I mean, we use a linear system and then make it unstable, and then that system is starting to oscillate. So these are the differences. In the switching oscillators, we usually use a nonlinear device to clap the signal and then again discharge the capacitor. So the linear oscillators could be a combination of RC signals, RC components, or LC components, or crystal components, what you've seen in the lab. Some of you maybe have done this in the lab, that we use a crystal oscillator to make a oscillator. And then we have another two types, and then these two types usually we use for the digital circuits. So these are mainly for digital. If I want to categorize them in terms of the frequency that they cover, so switching oscillators maybe are working up to hundreds of kilohertz. So these are up to, I don't know, 1 megahertz maybe, or less, because mainly they are working based on the op amps. So these are up to 1 megahertz. And then the linear oscillators, which are R and C, again, we are going up to maybe few megahertz, because they are working based on the op amps as well. But the LC oscillators, I mean, when we are using the L and C, then we are going up to tens of gigahertz. We can make an oscillator up to, I don't know, 60 gigahertz for the LC oscillator. And then the crystals, so crystals are very accurate. I mean, the advantage of using a crystal is that it has a very accurate, very high resolution accuracy, and For example, you can say that, okay, I want a crystal working at 32.768 kilohertz. So you can make it exactly at this, because they are using piezoelectric and quartz, so they could be quite accurate, but they are not that much high frequency. I mean, few versions of them which are available in high frequency, hundreds of megahertz or so, are available, but they are not cheap. So usually we are using crystals, and then you will see in the next lecture that we are using PLA to make higher frequencies out of them. Multipliers and PLAs, okay? All right. So this is what I mentioned last week, that a linear, yeah.
Last class you told that linear systems cannot make oscillators.
True.
So linear oscillators are different from linear systems.
Yeah, we have a linear system, but we add a nonlinearity to that one to make it oscillator. Yeah. So this is what we do. Yeah, it's a very good question. So it's in a linear system. This is what I want just to tell you, that linear system does not oscillate. You cannot make it oscillator. You can make it unstable, but this instability, I mean, it always diverge. But then we put a hinder for that, a limit for that, and then at that limit it stops, and then we can say that, okay, at this point, then it's oscillating up to this point, and then it starts to oscillate. So what I mentioned last week is that in a linear system with the zeros and poles like this, I mean, if the transfer function of a linear system Hs is the combination of, or the multiplication of these zeros and poles, then based on the position of these poles, we can say that the system is stable, unstable, or oscillating. Okay, a linear system. So we define the unstable region in the right plane and a stable region in the left plane of the S-plane. So this is your S-plane, and S equals to sigma plus j omega. And with the position of these poles in the S-plane, we can say that, okay, this system is stable or unstable or oscillating. In the region 1, if we have a pole in the region 1, the system is stable. I mean that if we have an initial condition for this system, this is the time domain. So in the first region, then if we have a initial condition for the system, then this initial condition, after a while, it's going to be like this. I mean, it's going to get 0, or for example, it's going to be like this. Okay? I mean, the system will be stable. At the end of the day, in the long term, it's stable. But if we have a, and then these two, okay, what's the difference between these two? I mean, why one of them has a oscillation, kind of oscillation, and the other one does not have?
That would depend on the position of the poles.
Yeah, the position of the poles. What's the difference between the position of the poles in case A and...
The one that's at the
The first
vertical
case
axis
is over
where
damped,
the...
second one is critically damped.
Yeah, true. So if your poles, for example, be here or here, then we have something like this. I mean, it's case B. And if you have a pole at this position, then it's like this. I mean, it's position A. So this is A, and these two are B. Okay. So this is, and then for the case 2, again we have two. So it could be like this. I mean, it's diverging, or it could be like this. And then increasing and increasing. Again, at the end of the day, we have an unstable system. So this is actually the T. Again, if the poles, so this is A, and this is, so just put this is C, and this is D. So if the poles are at C and at D. So the response of the system we can write down as A, I mean in the time y of t equals to A e to the power sigma plus j omega t. So if this sigma is negative, I mean if we are in the left plane, then definitely this is decaying sigma. If omega is 0, then as your friend said, for example, this is critically down. If omega is not 0, then we have a kind of oscillation, and at the end of the day, we get stable. If sigma is positive, definitely our signal, I mean our output is going to increase by elapsing time. Okay? But if sigma equals to 0, I mean the condition that I mentioned here as condition number 3. So if sigma is equal to 0, it means that we can have oscillation. But usually we cannot. I mean, in the reality, we cannot. Because by changing the condition of the system, which is changing always because of the noise, then this point or this point is moving either to the left hand or to the right hand side of the plane. Okay? And as soon as it gets to the right hand, then the system gets unstable. Or as soon as it goes to the left hand side, then again the system is going to be stable, and your signal will be damped. So usually for making oscillator, we are trying to work in this condition, but we put a limitation to our systems that our output cannot go further than that. So this is how oscillator works. And then after a while, then your system gets saturated, and then the oscillation happens. This is how we make an oscillator. Clear? All right. So we can show a system that has a feedback like this. I mean, this is a system with a feedback. Okay. So we get a feedback from the output, and then pass it through another network, and then add it to the input. This addition could be positive or negative. I mean, we can have a positive feedback or negative feedback. Usually we use negative feedback to control our system. I mean, we use a negative feedback to have a control on our system. You learn this in your control course, all right? But if we write down the transfer function of the whole system, I mean the system with the feedback, we can see that the output relating to the input is coming from this formula. I mean the h of j omega divided by y. If your feedback is negative, then this sign is positive. If your feedback is positive, then this sign is negative. You can write it down by yourself and see that, okay, this is correct or not. Okay? So with the negative feedback, the sign is positive. With the positive feedback, the sign is negative. To make this system oscillator, it means that we should not have any V in. I mean, a system without any input is going to generate a signal for you. Start oscillating and generate a signal for you. So we assume that there is no V in. And then this condition, when this condition can generate a signal for you, when the denominator equals to 0. I mean, the condition that a system is oscillating is that GH equals to 1. So G of S, H of S should be equal to. So this is the condition that we have for the oscillation. And then what does it mean? It means that the amplitude of G of S multiplied by amplitude of H of S should be 1. And then the argument of these two should be 0. And we say that, okay, this is the criterion that we say, Barkhausen criterion. In different type of oscillators that we are going to cover, we always calculate to reach this condition. So this is the condition that we assume that the system is going to be oscillator. So any small input, I mean, if we have a noise at the input, we usually have a noise at the input. If we assume that there is a small amount of noise at the input, then by this criterion, then we will have an output. Okay? All right. So the first type of the oscillators that we are going to cover is the switching oscillators. So switching oscillators usually use negative feedback. So in the switching oscillators, we are using negative feedback. Although in the negative feedback, we are using negative feedback most of the time for controlling the system, but there are situations that we can use a negative feedback, and then this negative feedback leads to an oscillation. One of them is, okay, and then the other name for the switching oscillators, usually in the literature, they are calling them relaxation oscillators, so they are the same. I mean, if somewhere you see that there is a dimension relaxation oscillator, it means that it's a switching oscillator. So this is one type of the relaxation oscillators. We have a feedback from our output to our input. I mean, a negative feedback to our input. We are using a charging or discharging component, and then try to charge and discharge this during the time, and then out of that we are making an oscillator. So this is the whole structure of a switching oscillator. I mean, we usually use a very nonlinear device like a comparator or for example, what do you call this? The hysteresis amplifier, and then by charging discharging circuit, we usually charge this circuit, and then we get a negative feedback, and then change the situation of this comparator, and then again discharge it. So this is how the system is working. So I will explain this here, maybe by equations is easier. The main nonlinearity of this device is that it is going to get saturated in the output by its VCC and VSS. I mean, the nonlinearity of this device is coming that from the point that the output of this device cannot reach more than the VCC or cannot go below the VSS. So this is the nonlinear situation that we say. Okay? And then using or abusing this nonlinearity, then we can make an oscillator. Assume that the op amp is biased with the plus minus VDD. I mean that the maximum voltage that the op amp can get is the VDD, and the minimum is minus VDD. Okay, so we are biasing this op amp with these two rails. So if you look at this path, I mean, if you look at this path, then the voltage at this point, or the V plus, can easily found that it comes from this one. Okay, no current is going into the op amp, and then the voltage at the V plus is just the voltage divider between these two resistors. Okay. And then the voltage for the negative path, also you can write down the current which is going into this line and the current which is coming into this. If you equalize these two, then the voltage and the negative feedback is coming from this formula. Okay. So assume that at the t equal to t naught, I mean sometimes at the middle of the time, not at t equal to 0, because at t equal to 0 the system is not oscillator anymore. So the system starts to increasing and then get clipped to see that what's the frequency for this oscillation. So we should get a middle point. So at the middle point, assume that the output for the system is stable, and this stability is coming from, I mean, the voltage that we have at this point is exactly equal to the voltage exact at this point. So the V minus is coming from this formula. Okay, for the op amp, the V plus and V minus could be equal, and then it comes from this formula. So the V minus equals to this one.
Why it has the opposite sign?
Sorry?
Why it had opposite sign?
Has the opposite sign because I assume that the output voltage is minus VDD. Okay, I mean it is stable at this point. Okay. I mean the capacitor is fully discharged, and then we are going to the charging period. All right. So when we are going to the charging period, the output of this is stable at minus VDD. And after charging period, then the output of this is stable at plus VDD. Okay? So assume that we are starting a charging period. And then the output is minus VDD. Then from this equation, if you write down the V minus after T naught, I mean at T naught we assume that the voltage at the V minus equals to this value, and then the voltage is increasing or charging based on this equation. And if you write down based on this equation, then you will see that in the charging period, the V minus is following this equation. Are you following me? No? I can just write down here. So if you do the integral on this, see, this is a differential equation, and it has two answers. And based on I mean, if you solve this differential equation based on dV minus, so dV minus, and then this is V minus. So if you want to find a solution for this differential equation, then you will reach this one. You have to find, you know how to solve the differential equation. Okay. So the differential equation has two answers. This is one answer, this is another answer. Okay? And then it has an initial condition, which is you have to put and then find the values for the differential equation solutions. Okay?
Excuse me. Can you explain, Seven, in the charging where how did this equation came?
This equation.
Yeah.
This equation is coming from this equation. So this is a differential equation. And you have to solve this differential equation to find, I mean, the solution of this differential equation is this one.
And VDD is...
VDD is the bias.
Yeah, it's the V out at the beginning. Not the zero.
At the beginning, which one?
VDD is bias.
No, the V out assumed to be minus VDD. This is what you just asked. V out is minus VDD. Okay? In the discharging, I mean in the charging period, the initial condition is minus VDD in the V out. So you have to put the V out minus VDD and then solve this differential equation. Clear? And then, okay, when the voltage at this point, I mean when this capacitor is getting charged and the voltage at this point is greater than this one or equal to this one, then the function of this op amp is changes. I mean the output, then if this one greater than this one, then the output will be plus, something like that. Okay, so we have to find the position or the time that these two are getting equal. So the voltage at V plus equals to this, and the voltage at V minus is equal to this, and then you find that the T1 is coming from this formula. So after how long? I mean, if the time base is T naught, after how long this situation is changing, and then this is the half of this period. So this is if here is T naught, then here is T1, and this is the half of the period. Exactly the same thing we have here in the discharging period. So we assume that our output is now, when the function of this op amp changes, then the output is changing to V plus. I mean, it is stacking at the higher rail. So again, if you solve that differential equation, you will reach this formula. And if you equate these two equations, we will find that after this amount of time, then the situation of discharging is finished. So this one here is T2. And then the whole period is the actually T2 minus, I think, T naught. This is not correct. This is T naught. Is T2 minus T naught. And is 2 tau ln of this one. So what I did is that I assume that the system is stable. Assume that the system is stable at the beginning. The output is connected to the negative rail. The capacitor is fully discharged. And then I started to calculate everything. So two phases. The first phase is the charging of the capacitor. And then when the voltage of the capacitor reaches to the voltage at the positive, then the situation of this op amp is changing. I mean, the output of the op amp changing, and then the discharging period starts. Okay? I found the time that we need to charge the capacitor to the value of, I mean, from 0 to the value of V plus point. And then I found the time that we need to discharge that capacitor to, again, the 0 value. Okay? I think you had this circuit before. You should remember this. No, not in this unit. Previously. Well, what do we call this? This kind of circuit? I don't know that you had it in your electronic or not, because if we had it, it's A-stable. Yeah, it's A-stable multivibrator that we usually make it with 555, but we can make it with the op amp as well. So if we, so the thing that what you can change here, if the value for this R1 and R2 are not equal, I'm not sure this is correct or not. I think this is correct. Yeah. If R1 and R2 are not equal, then the T clock is changing. How we can change this? Yeah. So actually in this circuit, I think we cannot change the duty cycle. But with 555, we can change the duty cycle of this. I mean the charging time and discharging time, then we can change those two. But here now, because the charging time and discharging time are coming from the same formula. But with 555, we were able to do this. Yep. So here, I said that this is the block diagram of a relaxation oscillator. And then this relaxation oscillator, what we use for charging is just a simple resistor. I mean, this circuit is a simple resistor, and then we just get a feedback from this to our comparator to see that in which state we should change the state of the comparator. All right. As I said, the switching oscillator is working for low frequency. But in the high frequency, we usually use linear oscillators, and mainly the L and C linear oscillators. Although we can use a RC. So, as I said, a linear circuit itself cannot oscillate. Okay, so what we do is that we use a linear circuit, but then we add a nonlinear element into this circuit. For example, a nonlinear element could be a transistor. A transistor has a linear region, and then it can go to a nonlinear region. So we can use, for example, a single transistor to make the system in some times nonlinear, and then at those times, then we are going to clip the signal and make an oscillator. So a purely linear circuit is never oscillate. And then when your poles are on the imaginary axis, then we say that the system is infinitely sensitive. It means that by adding a simple noise, then we can be stable or unstable. And then the system could get damp or could diverge. Okay, so here but you should always consider that the Barkhausen criterion, if this one is HS and for example this one is GS, then this HS multiplied by GS should be 1. So this is what we are always looking for. If our system itself has a gain of positive, then our feedback also, I mean the network in the feedback should have a gain of positive. If our system has a gain of negative, then our feedback also should have a gain of negative. So this is what you should consider. Sometimes a transistor can give you a gain of positive based on the point that you get the signal from, or it can give you a negative feedback and negative output. Okay. All right. So in linear systems, we usually use a positive feedback. I mean, the feedback that we get from the output is adding to the input. Again, okay, we call this circuit the Wien bridge oscillator. And then the nonlinearity of this system, I mean the nonlinearity that we add to this system to make it oscillator is that this op amp is getting saturated to its rail. So the nonlinearity that we have is that the op amp is getting saturated to its rail. Okay? So if we write down the gain of this system, I mean the gain of our linear system. So our linear system is, the gain of our linear system is coming from this formula. I mean the voltage at this point, the voltage of this point, which is equal to voltage of this point, always. So it is coming from this formula. And then if we write down the transfer function, I think it's not easy. I tried this by myself. It takes 1 page to find the transfer function of this one. But if we write down the transfer function of this, I mean if we, for example, replace all this c with the 1 over j omega c, I mean the z of c as this one, and then z of c again 1 over j omega c, and then write down the transfer function of this, then you will find that the transfer function of this system is Hs. And then the Barkhausen criteria says that the 1 minus KHS should equal to 0. Or KHS should equal to 1. And then based on this, we say that this condition should be satisfied if we want that this system is oscillating. Okay, so my question from you is that when this system can oscillate, I mean this based on this condition, what should happen that this system is unstable?
When the determinant is not equal to 0, then it becomes unstable.
Denominator. So denominator is never equal to 0 because it has a 1 here. Any clue?
On this slide, when k greater is
Okay, y. Okay, y. Yes, true. For k equal, for k greater than 3, y.
the middle term to be negative,
Okay.
so it can compensate the SCR square plus 1
Yeah.
go to 0.
Yeah. True. So if I want to write down this, then okay, you had that this k equals to 1 plus r2 divided by r1, okay? And then based on this, if we want to have a, and this is this SE equals to j omega. If we want to have any root for this equation to be in the unstable region, then we should have this 3 minus k, sorry, no, greater than 0. So less than 0. Because if this is less than 0, then we can say that this has a root in the unstable region. Is this clear? No. No, this is the condition of this system. This is the condition that I mentioned, that one. So the system, actually the whole system is Hs divided by 1 plus Gs Hs. So this is the whole system, okay? I mean, I want this to be equal 0. So forget about this part. Only this one should be 0. Because this is only the denominator of the main function. The denominator of the main function I put that equal to 0. Okay? And then the denominator of this function, if it wants to be 0, then this value should be less than 0. If we want to have a answer for this, so this value should be less than 0. A real answer for this. Is it clear? I mean, if we have a x2 plus ax plus b, if we want to this have an answer, then what should happen? So this one, if this one is negative, it definitely has an answer. Okay. Yeah.
Isn't it dependent upon the unit circle for the experiment?
Sorry.
If it is inside, if the points lie inside the unit circle, they're stable. Only when k is greater than 3, they will lie outside the unit circle.
See? Or you agree with me that the transfer function of the whole system, assume that this system has a gain of k, and in the feedback has a linear system or a nonlinear system which has a hs. Okay? So the transfer function of this system, the whole transfer function is k divided by 1 minus k hs. Okay? So this is the whole transfer function. And then based on the Barkhausen criterion, we say that 1 minus kh of s equal to 0. Then that one gives you the oscillation criteria. Okay? So 1 minus khs, you can find that this one. And then when you write down, it's equal to 0. So when it has a root, when we can say that, okay, this one has definitely a valid root, when this value is less than 0, negative. So this is what I can say. Okay, in the frequency domain, if we want to say that when something like this happens, we know that from here, we know that actually with negative feedback. If we have a negative feedback, then this is -1. If we have a positive feedback, then +1. If we have a negative feedback, it's -1. So k h omega should be -1. Okay? So usually we have a negative feedback. I mean, our system, the gain is negative, or it could be positive. For example, in a transistor, if we get a feedback from this point to the input, then this is negative feedback. If we get a feedback from this point to input, then this is positive feedback. So it could be different criteria. All right? So if we have a negative feedback, then this should be satisfied. And then it means that the phase of your system at the frequency of oscillation should be -180 degree, and the amplitude multiplied by the amplitude of the gain of the system should be greater or equal to 1. Why greater? Why greater? Usually we put it greater because the system has loss, and we need that the noise increase and then reach to the limiting point. So we should have a little bit positive gain. The total gain of the system should be a little positive, little more than 1, that the noise can increase and reaches to the saturation point.
So negative feedback, we get the positive gain.
Always it should be greater than 1. If you have a negative feedback, the phase is -180 degree. If you have a positive feedback, then it is 0. The phase is 0. But always these two should be greater than 1, a little bit greater than 1, that it lets the noise to improve and reaches the nonlinearity. Because if it is 1 or it is less than 1, then it does not work. Okay? Yeah, it is mentioned here then. For example, it should be greater than unity, otherwise the oscillation is marginal. Marginal means we cannot make sure that the oscillation will happen. Yeah, and then with the positive feedback, so everything is the same, just the angle should be 0 instead of 180 degree. So and then okay, what's the resonance frequency of this circuit? What's the resonance frequency of this one? I mean, if this equals to 0, then S equals to yeah, it is 1/RC, but you should find it. That's why I leave it to you. It is, yeah. So this circuit is oscillating at this frequency, 1/RC. And then by putting this 1/RC here, then we can find that I mean, if we put the S as 1 over RC, then we can find that based on this formula, we can find that the gain should be 1 over 3. I mean, the K should be 3. So if R2 equal to 2R1, then this is marginal case. So in marginal case, again, you see that if R2 is 2R1, the K is 3. So this is what exactly we found here, that K equals 3. So the K multiplied by H should always be greater than 1, a little bit greater than 1. Again, the RC linear oscillators are for low frequency. In the high frequency, we mainly use the LC oscillators or crystal oscillators. I mean, the feedback network that we use is kind of this circuit, or we can simply use a crystal that the model is something between these two. Okay, so the first one that has 1L and 2C, we call it Colpitts, and the second one we call it Hartley. There is no difference between these two. You can pick any of them to make a LC oscillator. They are almost the same. So if we write down the equation, for example, the transfer function for the Colpitts network. So the Colpitts network, V out over V in, you can find from this. It's easy to find. Just replace this with this one is LS, this is 1 over C2 omega. This is 1 over C1 omega J. This is J omega L. And then find V out over V in. It's a divider network. Okay, the voltage at this point divide based on the voltage at this point. And then you see that the transfer function is coming from this equation. So if we use it as a negative feedback, I mean, if we use this circuit in a negative feedback, then the phase shift for this system should be 180 degrees. I mean, if I found to see that at which frequency the phase shift of this system is 180 degree, you can simply say that this part, I mean this part plus this part should be 0. If this system wants to have a 180 degree phase shift. So it should not have a imaginary part. There should not be any imaginary point section in this formula. Then we can say that the phase is 180 degree or 0 degree, and then based on that we can select. So based on this, then we find that the omega naught equals to this, and then replacing this omega naught, we see that the gain of this system is minus C2 over C1.
So the two capacitors resemble the for
All of them. So this is the feedback network actually. We assume that this is our feedback network. This is our feedback network. So the feedback network itself, the phase should be minus 180 degrees if we use a negative feedback. Okay. We usually use this network and then connect it, for example, to an amplifier. So we have an amplifier that has a gain, and then based on the gain of that amplifier, we have to select this C2 and C1 that this criteria is correct. I mean, your amplifier has a gain of K, and your feedback system has a gain of minus C2 over C1. So we know what's the K, we know that what's the gain of our amplifier, we can calculate it. It's something GMRC, okay? And then based on that, we should select the value for the C2 and C1 that this criteria is correct. And then we have to find the value for this L, that this system is oscillating, for example, at 1 gigahertz. So these are how we should calculate all these, the components for our oscillator. So C2 and C1 are coming from the, this is exactly 1 over K, the gain of our amplifier. And then when we define these two numbers, we put it inside this, and we know that, okay, our system, we want to make oscillator at 500 megahertz, and then we calculate the value for L. The same thing we are doing for the Hartley oscillator. So again, if you write down that and then try to convince this condition, then we will find that the omega naught, which is the oscillation frequency, is coming from this equation, and then the gain of the network that we have, the gain of this network, the Hartley network, is coming from this equation. Again, based on the gain of your amplifier, you select the values for L1 and L2, and then you try to find the value for the capacitor to tune for the oscillation frequency that you want. So usually we use the Hartley as like this. We can look at the Hartley like this. Okay. So usually we use a transformer, and then by moving the position of this, your rail here, by moving the position of your rail, you can change the value for L2 over L1, okay, by tuning that rail. And then this capacitor C, you have to select for the resonant frequency. We can replace those two circuits, the Hartley and Colpitts, with a simple crystal. So crystal, you've seen in the lab that the model for the crystal we can write like this. Usually we use two capacitors here. Okay. So for example, C1 or C2 or something. Okay. So if the gain of your amplifier is 1, like the one that you've seen in the lab, so if the gain of the amplifier is 1, then you can simply select these C2 and C1 similar, and then the system is oscillating, because the gain should be, if this is equal to 1, K equal to 1, then the C2 and C1 should be similar. And then we can say that roughly, okay, this circuit is just a L, because this value is very small, this value is very small, and then we can say roughly it's a. This is an engineering assumption. You usually say that the crystal is a model with just a L, and then put two capacitors, and then, okay, this is now a Colpitts So crystals, because it has one CS and one CP, then it has two resonant frequencies. But these two resonant frequencies are very close to each other. I mean, if you look at the impedance of a crystal based on the omega, then you see that it has one resonance frequency here and one resonance frequency here. I mean, at 2 points, it gives you the impedance equal to 0. Okay? So at omega S and omega P, at both you can have an impedance of 0. But these two are very close to each other. And then based on these two, we find these two Q factors. This is the question for the exercise. I will solve this, how we are reaching these two there. And then how we find the omega S and omega P. So first we need to write down the Z for the crystal oscillator, and then based our assumptions that, okay, in one case we put the CS negligible and the other case the CP negligible, and then try to find these two resonance frequencies. So the Q factors are very close, maybe just 1% different, and then we can say that both of them are almost the same. One of them is exactly this one, but the other one has some more terms. We will see in the exercise. So the crystals, actually the main advantage of the crystals are the Q factor. They can give you a Q factor more than 100. And then it means that when you are, what's the meaning of Q factor? Q factor means when you are looking at the oscillator spectrum, so you want to see a single tone at this. I mean, at this point, for example, your amplitude is A and the rest is 0. But if the Q factor is not infinite, so this is the Q factor infinite. But the Q factor, if the Q factor is not infinite, you see something like this. I mean, so your oscillator has more 3D bandwidths, which we are not interested, because then, for example, if you multiply this signal as the LO to your baseband signal, then the bandwidths that you are occupying is more than the bandwidths of your baseband signal, because this one has its own bandwidths. But if it is only one signal, I mean, if it is only one single tone, then exactly the bandwidths in the RF and bandwidths in the IF are the same, and also the recovery of the signal is much easier. Okay? So we call this phase noise of the oscillator. So we are always interested that the phase noise of our oscillator is as low as possible. Okay? And because of that, crystal oscillators are using, because they have high Q factors here in this circuit. So these are, for example, can come from the resistance of this one, can come from the resistance, I mean the equivalent resistance of this capacitor or this one, and the whole of the whole thing we model with this R. Okay? But usually, especially in the high frequencies, the series resistance of an inductor or the series or parallel resistance of the capacitors are high. So the Q factor then decreasing, and then the phase noise increasing. So we usually, for the high frequency, we use crystal oscillators and then the PLLs to achieve a high performance local oscillator. So if we want to show few examples of a real oscillator, so we have a network. So this is our network HS, and then, or for example, if I want to be compatible with those, then I can say that this is our network which has a gain of K, and then this is our HS. And then I got a feedback and then add it again to the input. This is a Hartley oscillator, and we just saw that, okay, this is the frequency, resonance frequency. The value for the L1 and L2 are coming from the gain of this transistor. So we have one exercise to see that how we can calculate the values for the L1, L2, and C. Okay. And then in the Colpitts oscillator, again, we have a feedback network and your transistor, which gives you a gain of K. And then again, we get feedback to the input. So you see that this system does not have any input. When you connect the VCC and power it up, because of the noise that is coming into this circuit, and then it starts oscillating, and then it gives you a signal. So there is no need of adding any AC signal to this. So it's just amplify the noise, and then based on this frequency selective circuit, the noise, only that component of the noise which is passing through this frequency selective circuit is amplifying, and then it oscillates at that frequency. For a crystal oscillator, again, we have a network. So this is your network, and then we can say that, all right, this is almost the L and the C, and this one another C, and done. So we get the feedback to the output, to the input, from output to the input. So the base is your input, and then the collector is your output. So I get a feedback from output to input. And this system has a gain of, I don't know, what's the gain of this transistor? In this configuration, I mean, if this is the input and this is the output, what's the gain of this transistor? What's VO over VI? If here is VI and here is VO, are all in parallel with R, and R is dominant. Sorry? Okay. Then based on this value, I mean, this is your K. And you see that your K is a negative number. Then K HS should be 1, and then HS should be 180 degrees. That's what we saw. So if we make one of these capacitors programmable or variable, I mean, if we can change one of the capacitors, then we can change the resonant frequency, and then we call it voltage control oscillators. So voltage control oscillators means that instead of using a simple capacitor, we use a varactor. So varactor is the capacitance of a varactor changes based on the voltage across the two terminals. Okay? So by changing the voltage across the two terminals, then we can change the capacitor, and by changing the capacitor, we can change the resonant frequency. So it's very good if you want to make a oscillator that sweep, for example, from frequency 1 to frequency 2, then you can simply change the voltage from point V1 to V2, and then the output frequency is changing from F1 to F2. This is how VCO is working. So it's very useful component in the radars. So in the radars, usually we are interested to make wideband signals and then for different frequencies. So by changing the voltage, simply you can change the output frequency of your oscillator. Usually, so varactor is a kind of diode actually. So it's a diode, a reverse bias diode. So a reverse bias diode, by changing the voltage across these 2 points, mainly we change the thickness of the depletion layer, and by changing the depletion layer, then the capacitance is changing. The capacitance between these 2 terminals is changing. So this is how it works. All right. Okay. So we can have 10 minutes break and then we can continue on this. Yes.
Positive feedback, you got negative 1/1. Feedback.
So this is what I mentioned here in the Barkhausen. When you get positive feedback, this one is negative. When you get negative feedback, this is positive. If you write down this, you will see that.
So for the whole system?
Yeah. So for the whole system, if you add these 2 together, if you write it down, you will reach to this. Yeah.
For before, when you got that RF amplifier L, right, and then you got some IC blockage,
It's a blockage like
RF package like
RF chuck. Yeah.
Yeah, and then another one over here. So this one, like when you
Okay, shall we continue? So if we look at the small signal model for an oscillator, so this is a Colpitts or Hartley? This oscillator is Colpitts or Hartley, or none of them? Hartley? Why? Why? Yeah, so it's Colpitts because it has two capacitors and one inductor. So this is Colpitts. Okay. And then where is the, the feedback is coming from where to where? So we have a feedback from here to here. True. So we get the feedback from the collector to emitter. Is it true? No. Okay. So it's to here. Then what's this one? What's the purpose of this capacitor?
These are the bypass or DC.
DC blocking. Yeah. This is the DC blocking capacitor, and then in the AC analysis, you can just get rid of that. Okay. So we get a feedback from the collector to the base, and it means that, all right, this is our input, this is our output, and then the gain of this is this transistor is the GM minus GMR. So the gain of this circuit should be 1 over minus GMR, then the gain of the transistor and the gain of the feedback network equals to 1 times that one equal to 1. Okay, this is how we are going to solve this. If we write down the small model and then we assume that the low frequency model of that one, so no C pi, no C mu, and then the R pi and R naught also is very high. So a simple circuit like that is, like this, that we have a V pi at your base, and then the current is the GMV pi, so this is your load, and then the C1, C2, and your L, and this is your L. Okay. So a KCL at this point, this current, and this current, we can see that. So one current is the GMV pi. One current is coming from this voltage multiplied by the conductance of your collector, which is 1 over R plus SC1. And then another current is coming from this one. The current which is passing through this capacitor is similar to the current which is passing through this inductor, no difference. So this is the current 1, 2, and 3. So this is 1, 2, and 3. All right? So this is one equation. And then another KCL at the base. We can say that, okay, this current equals to the V out minus V pi divided by the impedance of this inductor. And after eliminating the VO, we can find that the equation for the small signal model is coming from here. And then to make this correct, then the real part should be equal to 0 and the imaginary part should be equal to 0 at the same time. Okay, so then we have two equations, one for the real part and one for the imaginary part. And based on those, we find the resonance frequency and we find what's the value for the gain. And this is what I told you, that the gain of the transistor is GMR. So the gain of your feedback network is C2 over C1, which is 1 over GMR.
The KCL equation 2 of them represent the denominator part of the closed loop controller, right?
No. I just write down the small signal model. I didn't do anything. I just write down the small.
Everything to be 0 at the end. Yeah.
I just omit the VO from these two equations.
Yeah, but at the end you set it to be 0. So the whole thing.
Because this is equal to 0.
Oh, okay.
I just replaced the VO from here. Okay? I didn't do anything. I just replaced it and then I said that to make this happening, these two conditions should be satisfied from the small signal model. Exactly what we got from the previous section, that the gain should be C2 over C1. And okay, I have one question from you actually. And so here, I want to see that. Yeah. So here we say that it is minus C2 over C1. And then the amplifier gain is also minus GMR. So just, the minus C2 over C1 should be GMR, something like that. And you find this. And usually I said that the gain of your amplifier and the gain of your feedback network, this multiplied by that should be greater than 1. So this is the condition that you should take care. But it should be a slightly, if we find this value, because we know that what's the value for the GM, we know that the biasing of this transistor, and then we know that what's the value for GM is IC over VT. And based on that, we should select the capacitors 2 and capacitor 1, and then again based on the frequency that we want our circuit oscillate, we can select the L, and then done. We designed our oscillator. Okay? Yeah. Slightly higher than. We can okay, this is Hartley or Colpitts. Actually, it's mentioned here. Okay, so it's simple. We can use it like this. Instead of this amplifier, which is like this, so instead of this one, we can use this structure. To write down the small signal for this small signal model, again, this is your transistor, and then here is your V pi. I mean, from here to here is your V pi. And then I assumed again that the C pi, C mu, R pi, and RO is not are negligible, and it's not in our model. And then we write down the equations to find the oscillation frequency and actually the Barkhausen criteria. So we can say that the I1 equals to V pi multiplied by the conductance of the capacitor 2. I2 is actually I2 here is the current which is passing through this one, and the voltage at this point is the V pi divided by V. So at this point, if we assume that this voltage is V, so the I2 is V plus V pi divided by this impedance. I3 is simply come from this equation, the voltage across the impedance, and also we know that I3 equals to I1 is I1 plus this current, so I3 is I1 plus this current, which is GMV pi, and I1 equals to minus I2. Based on all these, again, we can find one equation. Put the imaginary and real parts equal to 0. Again, we find the gain and the resonant frequency. So the resonant frequency is C1 plus C2 LC1 C2, and this time we get this, that C1 C2 should be less than GM over omega 2R. So these are the two conditions that we should satisfy to make this circuit oscillating at the frequency of omega. This is the whole circuit that we have for an oscillator. So for your design project, you need to design a local oscillator to feed your receiver. So this is something that you have to design. You need to design a transistor, bias the transistor with these two, mainly with these two, and make a VBE that this transistor is on. Okay, and then by selecting this R3 and R4, then we can select the DC voltage of our oscillator. I mean, our oscillator is like this. If you look at the output of your oscillator, it has a DC voltage, and then it has a oscillation on top of that. So we should pick this point by selecting this R3 and R4. All right, and then get the output. So R3 and R4 is for adjusting the offset. And then selecting the L, C1 and C2 based on the equations that we achieved just here. So this circuit is exactly what I showed there. I mean, it's this circuit. Okay. To make a VCO, I mean a oscillator that the output frequency changes, we have a control on the output frequency, then we can put a Colpitts and then these two capacitors, actually the voltage across these two capacitors, we are changing by this tuning bias. So by changing this voltage, the capacitance of these two capacitors are changing, and definitely the resonant frequency coming from this circuit is changing. The capacitance of a varactor is coming from this formula. I mean, if the V bias is equal to 0, then it has an initial capacitance. So it has always a capacitance, I don't know, a value. And then by increasing the voltage, then this capacitance is changing. Actually reducing. So the output, the overall capacitance is decreasing. There are many varactors available in the commercial shelf for low frequency and high frequency with different packages. And then this VDIF is the actually I told you that it's a diode. So this VDIF is coming from that diode, the threshold voltage of the diode.
V by S cannot exceed that value. Because if it exceeds, then it's going to be
Negative. Yeah, I understand your point. I should check. I don't know. Because usually you can exceed that, but I don't know that what will happen if he exceeds. So it seems that if he exceeds, then I don't know. This is not capacitor anymore. It's going to be a resistor or something because it's C over J something. Okay, I should check. But usually we use this formula. I should check in one of the data sheets to see that what will happen if we pass the VDIF. I'll tell you that next week. Okay. We can use a differential amplifier like this and then make an oscillator. Okay? This is very useful, and I believe because most of the time, as you saw, for example, in your mixers, your double balanced mixers or single balanced mixers, they need a differential LO. You remember that in a double balanced mixer, for example, we had a transconductance stage, and then we had a and this is LO and this is LO naught. We have a two-stage switch, and then we got out of these two our IF signal. Okay. So, for example, in the mixers, most of the mixers, single balance or double balance, no difference. We need a differential LO. So it's good to make a differential oscillator. So this is the application. I mean, the application of the differential oscillator is for the double balance mixer. And in your design project also you need a differential output. You can make a differential like this, or you can make a circuit like this, and then after this put another stage to get a differential signal. I mean, then you can put another transistor and then get one output from here and one output from here, and then it's differential because the output here and here are the same gain and different sign. True? You can use this structure, or you can simply make a differential oscillator. And then for the differential oscillator, we can get a feedback from the output of the transistor 1 to the input transistor 2, and from output transistor 2 to the input transistor 1. So it's very simple. And usually we put this as a varactor, and then change the output frequency and keep these two constant. This is Colpitts or Hartley? Hartley, yep. All right, so it's mentioned that after this oscillator, I mean, when we get the output from these 2 points, then we want to connect it to our load. But when we connect it to our load always has the input capacitance, always has the inductance or resistance, and then the frequency that we made is changing. So this is the problem that we usually get. So to avoid this, we usually put a buffer, always put a buffer after our oscillator. Then we are going to isolate our oscillator from the parasitics coming from the next stage. This is what I mentioned here, that, for example, here we should put a buffer, and then out of that buffer we get the signal from our oscillator. Then the parasitics of the mixer or the parasitics of the next stage does not affect the resonant frequency that you get from your oscillator. I mean, you design your oscillator for L, C1, and C2, but then your C2 is in parallel with the C input of the next stage, and then it changes. So to avoid that, we put a buffer and then design. And then when our design completed, then by adding any circuit at the output of that buffer, it doesn't change anymore. All right. So two applications actually for the oscillators. We can use modulators based on the oscillators simply. So if we, so this is a FM modulator. This circuit is a FM modulator or FSK modulator. How does it work? So by changing, I mean, if you put a voltage here and this voltage is changing, this is your data and your data is changing. For example, your data is like this and then like this, something, digital data. And this is at the level 1 and level 2, or level 0 and level 1, okay? At level 1, the voltage of this varactor is something, so it is resonating in one frequency. And when the level changes to, I mean the digital value changes to 1, then the voltage across this varactor, I mean the varactor CV is changing, and then it generates another frequency. So then it's a FM signal. 0 making one frequency, 1 making another frequency. And the output, I mean the output voltage that you receive is actually a combination of the output of two oscillators. And you can modulate your signal. The resonant frequency of both of them are coming from the L, C1, C2, and CV. And this CV is changing, for example, between CV1 and CV2 based on the voltage 1 or 0. Okay? The frequency of?
The voltage data, only the voltage level affects the capacitance.
True.
Not the frequency. So however long the symbol is.
Yes. Actually, this could be a problem, because if, for example, the voltage that you are generating is not saturated, I mean this V data is not saturated. If this data is saturated at the top and bottom, then everything is fine. But if it's not saturated and then it changes, then the frequency which is going out is changing. I mean, you are expecting to send your data at F1 and F2, but then it's go to F prime 1 and, for example, F prime 2. Yeah. But if we make sure that these two levels, I mean the level 1 and level 0 are not changing and exactly stuck at one point, then it's fine. So we can, all right, I have few questions for you here. What's the purpose of this capacitor, CDC? I mean, if we don't put that CDC, what will happen? No. The varactor's capacitance is controlling by this voltage. Prevent? So why we want to prevent DC current here? I mean, if I don't put this capacitor, what will happen? If I don't put the CDC in series with the L1, the bias, no, there is no bias there. I mean, then you are grounding the base of your transistor. There is no DC voltage there, then your transistor is not get biased. Okay? So to prevent that this point is because this L is 0 in DC. Okay, it's short circuit in DC. If you don't put this capacitor, then you cannot bias your transistor. I mean, this point will be 0. Okay? And then, so you know that why we put this RF chalk, and you know that why we put this DC block. We already mentioned that this RF chalk is for preventing the AC signal going to VCC, and the DC block is to prevent the DC point that we have at this point to go to the next stage or affect the next stage, or from the next stage to our stage. Okay?
If the AC signal go through the R1 to the VCC?
Yes, it's going. It's better to put a RF chalk there. I mean, it's better to put one RF chalk here. Yeah. All right. So in the second circuit, I mean in the bottom one, we have a kind of similar. Okay, here, what's the purpose of the R3 and R4? What was your answer? Yes, true. To tune the output offset, actually. So we can tune the offset. This one?
Yeah.
So this is your L. Actually, this is your L.
So even that affects the resonant frequency.
So this is your, so this is the main element of your resonator. So your resonator is like this. It is a L, and then it has a C2.
Is the C1, C2 and L1 forming a Colpit?
All of them, all three of them actually. So CV, C1, C2, and L1. In the bottom circuit, again, okay, we got a feedback from here to here. How does it work? Actually, if the V data is 0, okay, if the V data is 0, then this diode is open circuit, okay? Because this diode is not biased. If the data, I mean the voltage of the data is 0. So the diode is not biased and it's open circuit. So what we have in our circuit, we have the C3, C1, and C2 and L. But when our data is 1, then this is conducting, and then it emits the C3. So the resonant frequency changes to, for example, only we have C1, C2, and L. So by using this diode and by changing the value for the V data, we can change the output frequency. I mean, we can set that the C3 be in circuit or not to be in circuit. And then by changing that, it means that we can change the output frequency. So this is FSK actually. All right. We can make oscillators out of just a ring of inverters. So the inverter circuit is this one, a CMOS inverter. So a CMOS inverter is this one, and this CMOS inverter, definitely based on the technology that we use, has a delay. I mean, when we are changing the input, the output changes after a delay. So it depends on which process you are using, the delay is different, okay? And then if we use all of these together, I mean in cascade, and then get a feedback from the stage number N, and then again feed the stage number 1, then we can make an oscillator. What is the frequency? So the frequency is coming from this formula, and the N is the number of the stage numbers, and TD is the delay, inherent delay of the NOT gate, delay of the NOT. Okay. And then why it is 2? So the signal that is, yeah. So we have a signal here, for example, assume that it is 1, and then this one takes TD time to get here, and then here is 0, and then here is 1, and then here is 0, and then here is 1. So we have n TD delay that the signal propagates from this point to this point, and assume that this point is exactly. So NTD, the T equals to NTD takes that the stage, I mean the status of your output is changing. And then another NTD is again, it takes that the status returns back to the previous one. So if your state was 0, then it takes NTD to be 1, and then again NTD to be 0. So from here to here is 2 NTD. Okay, and the frequency is 2 NTD. The main thing here is that the N cannot be even, because if it's even, then it's not oscillating. I mean, it does not change the state. So it should always be odd, 1, 3, 5, 9. And because of that, we cannot maybe make a very precise value that we want. We can make something, but not that as precise as that one. So because of that, we usually use a crystal oscillator. This is what you've seen in the lab, that we use a crystal oscillator and then use this NOT as a buffer or amplifier. So this is a simple amplifier. We mainly use this as a digital gate, but we can use it as an amplifier because it's CMOS gate. And then by tuning these two capacitances, I mean the CA and CB, so this is CB, by CA and CB, this is your crystal oscillator, we can tune the resonance frequency that we want. The model inside the crystal is like this, what we just mentioned, and then we will see the Q factor for this in the exercise. It itself has a resonance frequency, but we can assume that, okay, it's just L. And then these two C's making a Colpitts amplifier, and it's a inverting amplifier. So inverting amplifier and the Colpitts, it just make a oscillator for you. Okay. Question? Okay. If it's clear, then we can solve the question for the assignment and then the questions for the mixer. Then if we get time, the questions for the oscillator. Okay. All right. Okay, so for the assignment one, in the first question we said that in the part A, we asked to find the voltage gain, the input impedance, and the output impedance. Okay, so as I said in the lecture, or as I said in the exercise 1, we can replace these two transistors with their equivalent impedance. Okay, so we have I just write it here again. We have a NPN base, collector, and emitter. So the equivalent impedance of this transistor from the base equal to R pi, from the emitter is 1 over GM in parallel with RO, and from the collector is RO. Okay, and if we have a transistor which has a impedance at the base, then the impedance from the base is RB plus R pi. The impedance from the collector is again RO, transistor, and then here base, and here is emitter. And then from the emitter side, it is RB divided by beta plus 1 plus 1 over GM. Okay. We had in the lecture that if we have a transistor and it has a, for example, inductor here, then the impedance that we see from this part is, I mean, if we want to move this to the base, then the equivalent is another L, and then this L is L beta plus 1. The same thing from the other side. I mean, if we have something in the base and we want to see the effect of that in the emitter, just divide it by beta plus 1 and put it there.
So the whole thing would be for the upper part and the lower part would be RB1 plus R or the
We will reach there. So for the upper part, then what you see from here is, I mean, if I mention that as R equal 1, for example, this is R equal 1. This R equal 1 is RB2 divided by beta plus 1 over GM1. Okay. So the GM1 and GM2 and GM3 are not equal. They are different because the biasing conditions could be different. I mean, the IC of this, because the current which is coming from this space and this space, even if you assume that they are the same, it's fine. But you should consider that they are not the same. Always they are not the same. All right. And then for this PNP transistor, so the same. We are looking into the emitter of that. Again, here is the emitter. And then the R, if I say that here is R equal 2, then this R equal 2 equals to RB1 divided by beta plus 1 plus 1 over GM2. The same. And then we can replace this one with this R equal 1, the upper network, and then the lower network with R equal 2. So the resistance or the impedance that we have in the collector is the RC plus R equal 1, and the impedance that we have in the emitter is RE plus R equal 2. Okay? So we have a, then we can just write down the, all right, we can just write down like this, that we have a impedance, another impedance, I call this ZE, I call this ZC, and here to VCC, and this is your V in, and this is your V out. I can write down that. And then you had this in your lecture. If you have a degenerative impedance in the emitter, then the gain, the big GM equals to 1 over GM3 3 plus ZE. Okay, this is your big GM. V out over V in, or AV, equals to big GM multiplied by your R in the collector, which is, I call it ZC. And this ZC also is your R out. So it says that what's the output impedance? It's ZC. And ZC is RC plus R equal 1. Okay? And just negative. Negative. Okay? And then the input impedance, or R in, again equal to R pi, I mean from here, it is R pi plus, if this impedance, which is ZC, is going into the base, beta plus 1 ZC. Say R pi 3, because R pi are also different. Easy. Usually we say that no, but if you assume that they are equal, it's fine. Yeah. Because the biasing conditions are different.
Ignore 1 by GM3 as compared to Z. And then the final
Can we what?
ignore 1 by GM3 as compared to ZE.
No, of course not.
Because this becomes a common integer and then it's minus RC by RE.
No, you can't. So then what's the... No, you cannot. Because in the degenerative transistor, I mean, when we put a degenerative load in the emitter or in the source, then it changes the GM of the transistor. You can assume that, for example, okay, RB is very small number, then instead of, I don't know, instead of RB divided beta plus 1 over GM, say that it's okay, only 1 over GM. This is acceptable because RB is usually small. But a complete solution is this. But sometimes we cannot assume something which is important. Okay. All right. So it takes five minutes. In the final exam, you should spend 5 minutes to drive this. If you draw the small signal model, a 10 stage of a small signal model, and try to solve this, it takes 1 day. Okay. You just need to replace the equivalent circuit for the transistors, if it is MOS or BJT, no difference, with their equivalent impedance. In low frequency, definitely it's resistor. In high frequency, you should consider the capacitors and these things as well. For example, I mean, instead of only R pi, it is R pi in parallel with C pi. Okay? All right, the second one. Again,
For GM, if you consider that GM is equal to IC over VA, then
GM is IC over VT.
VG, then is it a good consideration to say that because the IC is the same for the three transistors, and the GM of them are equal somehow? Not exactly.
Actually, IC are not the same because IC of these, I mean IC of the second transistor is IE of this first.
It's just one against beta. And
You are true. You are. Yes, we can say that, but I mean a complete solution is that okay, the biasing are not the same, and then this. But that one is acceptable. If you put all of them as 1 over GM, it's fine. Yeah. All right. In the second one, again, we put the equivalent for these three, and then solve the problem again. So for a MOS transistor, again, this is your gate, this is your source, and this is your drain. So for the gate, the input impedance is infinity. For the source, the input impedance again is 1 over GM in parallel with RO, and for the drain, it is again RO. Okay? So for the, if I say that this is R equal 3, this is R equal 4, and this is R equal 2, I mean the equivalent of these circuits, then for the R equal 2, so R equal 2 equals to 1 over GM2 in parallel with RO2. We are looking into the source.
So we're looking down.
This is source. This is source. The arrow is source. Always source. Arrow is always source.
So we should consider the correct direction.
Yes. So actually here is the source of the transistor M2. And then we are looking into the source of. I mean from the source of M2 we are looking into the transistor. So it is 1 over GM2 in parallel with R. So this is R equal 2. And then for the R equal 3, again we are looking into the source. So it is 1 over GM3 in parallel with RO3. Okay? And then for the R equal of 4, we are looking into the drain. Yeah. So it is R. RO4. And then R equal 3 and R equal 4 are in parallel. So the impedance in the top, if I put it, for example, Z of drain, then the Z of drain equals to RO3 in parallel RO4 in parallel 1 over GM3. Okay? And then the gain again equals to minus big GM ZD. I mean it is ZD divided by 1 over G. 1 over GM1 plus R equal 2. comes from here. ZD multiplied by GM.
Should it not be RO1? Like for ZD, RO
Sorry.
For RO1, we ignore it to be
parallel
infinity,
to
right?
RO4.
Yeah, it's in parallel with RO1.
For the first one,
You are right. It's in.
Otherwise, if we ignore RO1, everything will be much, much easier. But if we include RO1, everything messy.
See, here you can, for example, say RO2 is very high, and it's just 1 over GM2. I mean, this is correct. Here. I mean, this is just say it's 1 over GM2. And here it's 1 over GM3. Okay? And here is infinity. R equal 4 is infinity. Just assume that they are not there. Okay? Because they are very big. But if we want to assume that all of them are there, then it is in series with RO1. I mean that we have RO1. Yes, it is in series. But we can assume that there is nothing. Yeah. We assume that RO1 is very big. In parallel with RO1. I mean, these two are in parallel with RO1. So here is ZD RO1, if you want to. Okay, the second question. Sorry.
Why are we in the first sets?
In the first one. Oh, I'm sorry. It's ZE. Guys, it's ZE. It's not ZE. See, it's ZE.
That gain is the final gain that we based on that gain is obtained by considering, but not considering RO. So the gain itself, when you consider the big GM RO out, then we write down like that, then RO is not considered. If we consider RO, then the whole thing is considered. Not just
Yeah, you are right. Yes, you are right. Yes, because RO has an effect in the GM, big GM as well.
Yeah.
Yes, true.
That one is not considered.
You are true. So we assume that RO1 is infinity, because if we assume that RO1 is not infinity, then the big GM is changing as well. Yes, you are right. So then I...
So in the second part of the question 1, it's the gain is 1 over 2 minus 1 over 2.
I didn't calculate that parameter. So parameterized, if you assume that there is no RO, then this is 1 over GM divided by 2 over GM, it's 1 over 2. Yes, true. If you assume that all the GM are the same. I mean, if you assume that all the GM are the same. Okay. And for the other one, I mean, this is the gain at Y, at the point Y.
For the first exercise, all of the collectors are experiencing the same currents, same IC.
No, this is his question. I mean, we can assume, but the IC that we have in the collector one And I see that we have in collector 2, collector 3 is different because the collector 3 has a IC of this and IB as well. Two current, IE of the transistor, IE of the transistor 1 equals to IC of the transistor 2. But if we assume that beta is very high, which is the case, yes, we can say that they are the same and GM are the same, if we assume.
But they're all connected together in series.
They are in series, but one current is coming from the collector and one current is coming. Guys, this is your question as well. One current is coming from the collector and one current is coming from the base. And they add together and make the current in the emitter. Okay? And the gain at, guys, and the gain at X, at point X, is exactly the same as what we did in the class. So then you have to look at the impedance here, and the impedance here is 1 over G, I mean the impedance of the R equal 2 divided by the big GM. So this is the AV at Y. It is ZD multiplied by GM minus, and AV, where can I write? Here. AV of X equals to R equal to GM. AV at Y equals to minus ZD GM. And GM is calculating from this formula. I mean, 1 over GM plus R equal to. Okay, the second question. Second question, part A is easy. So part A, AV equals to V out divided by V in. Guys, V out divided by V in, and equals to minus Z2 divided by Z1. You are agree with me on this. So this one has a Z2, this one has a Z1, and then the gain of the op amp is Z minus Z2 over Z1, which is minus C1 over C2 and equals to minus 10. So if you have a network, the gain is minus 10. I mean, if we say that this network has a H of F, then amplitude of H of F is 10, always 10. Okay? And then here it is mentioned that the gain bandwidth equals to 4 megahertz. So gain times bandwidth is 4 megahertz. So the bandwidth equals to 4 megahertz divided by 10, which is 10 to the power 5. Okay? This is the bandwidth of your system. To calculate the noise, we have two sources of noise. So we have a network. So this is our network. It has an input at this point. Some of you get the input at this point. Why it's this point? We have a network. Input is here. For this configuration, input is here. I mean, the signal is coming to this input. It does not go to that input.
So, I mean, the overall network should include the feedback as well. Otherwise, it's going to be 3-port network. We probably have one.
No, assume I want to say this. I want to say that we have a noisy network. The name is op amp. Forget about the feedback, everything. We have a noisy network. The name is op amp. And we want to model it as a noiseless op amp and then refer the noise into the input. Where is the input? Input is here. Why here? Because I apply my signal, input signal to here. If I apply my signal to the positive, then the input is there. Okay? So you replace this with a noiseless input, and then it has a Vn and In to ground. And this is your out. So we have two sources of noise, Vn and In. To calculate the noise, maybe we should continue until 6. I'm sorry for that, but I want to finish this. For the Vn, so for the part B, first the noise of the Vn in the output. So the Vn equals to, Vn in 1, I say, is 20 nanovolt divided by a square root of hertz, okay? And then what's the equation for calculating the noise in the output? So Vn out, that's true if the gain is frequency independent and if the signal Vn is frequency independent, which is the case here. This is true. But totally so Vn out equals to integral Vn in squared Hf squared df. This is your S out, this is your S in, and this is the formula that you have. And integral should go from the FL to FH, the operating frequency of your system. So for the Vn in and HF, both of them are frequency independent. They simply can come out of the integral. And then for the first one,
don't we have to include the bandwidth as well within?
Yes, we do the integral over the bandwidths. Okay. So then the Vn out 1 squared equals to Vn in 1 squared Hf squared integral from DC to 400k df, which is f2 minus f1 simply. Okay. As you said, we can just multiply everything and done. Okay. So for this one, it is equal to 16 10 to the power minus 9 V squared. This is Vn squared, not Vn itself. Squared. All right? Is it clear up to here? For the second part, we have In which is equal to 0.01 picoampere. Is it clear? Up to here is clear. Okay. Picoampere per square root of hertz. Okay. And then again the Vn out 2. And Vn out 2 equals again integral 0 to 400k Vn into squared hf squared df. Okay, and then this Vn in is the current which is coming from this and passing through this capacitor here, which is C1. So the current which is, this is, if this is your In, then the Vn2 equals to In multiplied by 1 over j omega C1. And this is not frequency independent, so you should take the integral. You cannot simply multiply by the bandwidth. Okay? Then the Vn out 2 equals to all right, the value I calculated is 10 to the almost 10 to the power minus 5 integral of 0 to 400k 1 over f squared df, and this one equals to 1 over f, so 10 to the minus 5 1 over f from DC to 400k. And how? Okay. So I have one question from you. So definitely if you put f equal to 0, then this is infinity. Done. And it's very good. If you put f equal to 0 and it's infinity, then you get full mark. I mean, if you say that, okay, the answer of this is infinity, is correct and done. But the question is, that in the, we had flicker noise before, okay? We said that the flicker noise is dependent on the frequency, and the value for the flicker noise, I mean the V n is equals, I mean it is relative to 1 over f. And then again we get the integral for this one, I mean 1 over f df, and then we said that this is ln of f, again from, for example, fl to fh.